Today we're going to go beyond our old techniques that you learned back in Algebra 1 for solving systems of equations. The three old techniques that Algebra 1 taught us, the first one was graphing, and that was really not a very adequate method. If you tried to deal with this problem using the graphing method, you'd have some trouble graphing this first line because the x and y intercepts aren't particularly nice. You'd end up with some sort of descending line looking like this. And then if you tried to graph this one, at least the x and y intercepts are a little bit nicer. You'd get a nicer picture. But then trying to figure out where the point of intersection is really rough, especially if the point of intersection doesn't end up being some nice whole number coordinates that are easy to figure out. Back in Algebra 1, you also learned about the substitution method. In the substitution method, you might pick the second equation, and you might solve for x, and then plug in for x in the other equation, and then you would proceed from there. That should be a pretty familiar technique. A lot of people are rather fond of the substitution method and feel that they understand it pretty well. And then there's a third technique called elimination that you learn in Algebra 1. And in elimination, the technique works like this. You take your system of equations, and you do some setting up sort of prep work by maybe multiplying one or both of the equations times something. Like here, you might multiply the second equation times 2. And what you're trying to do when you're doing the setup there is you're trying to prepare the equations so that something will cancel out when you add them. Like here, you can add them up, you get 5x equals 15, and you would proceed from there. So the work continuing forward from each of these, I'm skipping because these are just reminders that you used to know these techniques. Well, here in Advanced Algebra, in Algebra 2, we learned two new techniques and two new models for solving systems of equations. We learned a technique called matrices, and we learned a technique called Cramer's rule. Cramer's rule has some pretty severe limitations, but some pretty cool advantages. The limitations are severe enough that we don't want to start with Cramer's rule. We got to save it for last. So our main topic for today, the new method for solving systems of equations we're going to be learning, is called matrices. So I have to begin this topic with a sort of unavoidable joke. We need to talk about what a matrix is. So of course there's the matrix and a matrix. Very different things. Math used to be a lot easier to teach before that movie came out. Now that that movie came out, everybody thinks they know what the matrix is, and that's not the same thing at all. So there on the left, the matrix from the movie. A matrix is a much more boring thing. Not nearly as many guns. Then the other question is, okay, what actually is the matrix? And I don't know about you, but when I first saw the Matrix movie, I had no idea. I saw it on opening night, had no idea what the matrix was. Mind blown. But a matrix is nowhere near as mind-blowing. Although no one can be told what the matrix is, I can tell you what a matrix is. So what a matrix is a very simple thing. All it is sort of a summarized, abbreviated way of describing a system of equations. And in particular, this one here is a way of simplifying or abbreviating this system of equations, where the first equation would be 3x plus 2y minus, should be using different letters there. So 3x plus 2y minus 5z equals 1. And then there would be a second equation, 4x plus 7y plus 6z equals negative 3. And then there would be a third equation, 2x plus y minus z equals 5. And if you look at the matrix and you look at the system, it's pretty obvious, I think, how this relates to this. So we are beginning with a technique that just looks like we're abbreviating how you write a system of equations. You write it with just the coefficients, and you don't distract yourself with x's, y's, and z's and unnecessary symbols. So that's a very slight improvement. But it's going to also lead us to some very different techniques entirely. In general, what we're going to be doing with matrices when we're trying to solve a matrix, solve a system of equations by turning it into a matrix, is we're going to be manipulating that grid of numbers in a very sort of mechanical fashion. So, what we need to learn to be able to work with matrices and solve systems of equations is we're going to need to learn some things called the matrix rules. And there are 3 rules. It's nice and cut and dried that way. There are just these 3 rules for what you're allowed to do with matrices. The first rule is probably the easiest one, but you don't get to use it a whole lot. It's a pretty rarely used rule. It says that you can swap 2 rows of a matrix. And if you realize that each row represents an equation, swapping rows just means you're changing the order of the equations, which that should obviously be legal. There's no reason why you would not be able to rearrange the order of equations, so of course you can rearrange the rows of a matrix. The second matrix rule is one that you use pretty often, a couple of times in each problem, I would say. And that's the one that says you can take a row and multiply by any non-zero number. Multiplying a row of a matrix is equivalent to multiplying an equation by something. And we do that a lot. We multiply equations by things all the time, so that should feel pretty natural as well. In fact, it may be so natural that you're willing to also consider taking a particular row and dividing by something. And of course, we do that all the time with equations too. We multiply an equation by 2, maybe we divide an equation by 5. That kind of thing is equivalent. If you can multiply, you can also divide. Those are both legal. Now the third rule is the one that you're going to use more often than any other rule. You'll use it several times in each and every problem that you work out. And, unfortunately, it's also the most complicated rule. It says, and you have to be very cautious about doing exactly what it says, you may add a multiple of one row to another row. And probably the most important thing to remember about that is the target row is the one that changes, not the one that you're starting from, not the row you multiplied. I'll show you some examples of that so that it'll make sense, because right now it's a little too abstract. Now these 3 rules, these are the only rules you need to know to work with matrices. And it's very simple, but that's not really why matrices are tricky. The analogy I like to use is it's kind of like learning to play chess. I can sit you down for 10 minutes and I can explain how the various pieces move in chess, even with the weird little like castling tricks and things, capturing en passant, and all the various little twists to the rules. Anybody can learn them in about 10 minutes. But you don't master chess. You don't know how to play chess just because you sat down and learned how the pieces move. Knowing the rules does not teach you the strategy, and the strategy is the hard part. And the same thing is going to be true with matrices. The strategy of matrices is to use those rules to start from a system of equations and end with a solution. And a solution is where you've got x equals something, y equals something, z equals something. So the first step is pretty obvious. If you've got a system of equations, your first step is to convert it into a matrix form. So you just rewrite it where all you're doing is you're writing down the coefficients. Oops, I say coefficients and for some reason I wrote x. So you write down the coefficients, put in that little vertical line to indicate where the equal sign is, and now you have it in matrix form. Same system of equations, you've really done nothing. Then you apply all the various rules. And that's the tricky part, because you may use the rules 12 different times or something, do a whole bunch of different operations. And when you're all done, here's what your target needs to look like. It needs to look like the matrix version of a solved system of equations. In other words, the top row needs to say x equals a number. And in matrix form, that would look like this, where you have 1 for the x coefficient and zeros for the y and the z coefficients. And then the second row would have to say y equals something, and that would look like this. 1 for the y coefficient and 0 for the x and z coefficients. And then you need to have a row for z equals something. So the finished off matrix, a finished, solved, completed matrix problem is going to have that diagonal of 1s with zeros everywhere else, and then the last column will be the numbers that constitute your answer. So, the strategy is going to take up all of our time. And I have some suggestions. And I'm going to call this advice because these are not rules. You are perfectly welcome to break these all you want because all they are is advice. My first suggestion is to focus on one column at a time. What that means is, don't try to make everything work all at once. Make, like, say, the first column look right, and then move your attention to the second column and work on that, and then move your attention to the third column, something like that. My second advice is, work on the columns left to right. So, when I say the first column, I mean the column that's on the far right, the far left, and then you move towards the right. So this here would be column 1, this here would be column 2, and so on. That's what I'm talking about. And then my third piece of advice is, as you are working in each column, your target that you should begin with is to get the appropriate 1 that that column needs to have first, and then get the zeros. So get the 1 first, then get the zeros. Okay, so let's work an example, because the strategy is too big picture. You don't know how the rules fit together. This advice doesn't really clarify until you actually see it in action. So let's work through an example, solving it by using the matrix rules. I think this will probably help you understand what the steps are supposed to look like. So first step, convert it into matrix form. So each row represents the coefficients of the variables and the numbers on the other side. Watch out for zeros, like if there isn't a particular letter, then that means it has a coefficient of 0. So you start with this. And then if you're following my advice, you look at the first column and you think about what your target is. Remember, your target is supposed to be 1, 0, 0 for that first column. So we're looking at this and it's 1, 2, 1, and that's not quite right. Well, we're going to have to fix that. So then, in that column, we try to get the 1 in the appropriate spot, up here at the top. Oh, hey, it's already a 1. Sometimes you're lucky. Then we want to get rid of the 2, and we want to get rid of the 1 below that. The way we do that is by using that third matrix rule I was talking about up at the top, the one that says you're allowed to add a multiple of one row to another. So what I'm going to do here is I'm going to take row 2, and I'm going to add -2 times row 1 to it. So what that's going to do is it's not going to change row 1. Row 1 is going to stay the same. The source doesn't change. Only the target changes. And the target is going to have each of its numbers changed by -2 times the first row. So like right here in the first entries, 1 times -2 gets added to 2. Well, 1 times -2 added to 2 makes 0. For this next entry, 1 times -2 gets added to -1. That makes -3. If the numbers are really big or complicated, then you might need to do scratch work for the arithmetic, but try as much as possible to do the arithmetic in your head. This next one here is -1 times -2, which is 2, added to 1, which makes +3. And don't forget you got to do it down here at the end as well. -4 times -2 is 8, added to 1, makes 9. When you're doing one matrix operation, you can often do a second one at the same time and save paper. So I'm also going to do a second matrix operation here, where I take row 3 and I add -1 times row 1 to it. So again, row 1 isn't changing. Row 3 is changing. The target is what changes. And here I'll have -1 added to 1, which is 0. -1 added to 0, which is -1. And double negative, -1 times -1 is 1, added to 4, which makes 5. And don't forget you got to do the last one as well. -1 times -4 makes 4, added to 15 makes 19. And look at our first column, 1, 0, 0. So we're sort of roughly 1/3 finished. We've got the first column looking good. We move one column over to the right, and now we're starting to look at the second column. So we looked at the first column first, now we're looking at the second column. And remember what the second column needs to look like. It needs to be 0, 1, 0. So 0 needs to be there, this needs to be 1, this needs to be a 0. And in the advice I'm giving you, I suggest you get the 1 first. So I want to turn this -3 into a +1. There are a couple of different ways I could do that, but I think the easiest way to do that is to use the second matrix rule that says you can multiply or you can divide a row by anything you want. So I'm going to take row 2 and I'm going to divide everything by 3. So row 1 isn't changing. I didn't do anything to it, so it's still exactly the same as it was a second ago. Row 3 isn't changing. It's exactly the same as it was a second ago. But row 2 is changing. I've got to take all 4 of those numbers and for each one of them divide by -3. Well, 0 divided by -3 is still 0, so my first column still looks good. -3 times -3 is +1, and that was kind of the purpose, was to make that happen. But then I've got these side effects. I've got to work out these other numbers. 3 divided by -3, 9 divided by -3. The sort of side effects of making the center number a 1 was that those numbers are now changed from what they used to be. So I got the 1 right there in the middle, but the numbers above and below it need to be zeros. Here's how I'm going to accomplish it. For row 1, I'm going to add -1 times row 2, and that'll get rid of that 1 up there, because 1 times -1 added to 1 will make 0. And for row 3, I'm going to add just 1 times row 2, and that's perfectly legal. You can multiply by 1. So 1 times that added to that will make that -1 at the bottom turn into a 0 as well. But don't forget, you're also doing all the numbers in this center row. You're doing the 0 and the 1 and the -1 and the -3. All of those numbers have to get multiplied and added. Well, since the first number is a 0, 0 times -1 is not going to change anything when you add it. And 0 times +1 when you add to 0 is not going to change it. So that first number being a 0 makes the arithmetic very simple. For the second column here, 1 times -1 added to 1 makes 0. 1 times +1 added to -1 also makes 0, so second column looks good. And now we got to finish the rest of the side effects of the arithmetic we were doing. 1 times -1 is +1. Added to -1 makes 0 up there. That's an unintentional 0. Sometimes they happen by accident. -1 times +1 is -1. Added to 5 makes 4. And then for the last two numbers here, -3 times -1 is 3. Added to -4 makes -1. And -3 times +1 is -3. Add that to 19, you get 16. So check where we are. The first column looks the way we want it to look. The second column looks the way we want it to look. So our attention is now going to go to the third column, and we want to make it look the way we want it to look. So for the third column, we want it to say 0, 0, 1. It needs to have a 1 at the bottom and zeros above it. Okay, that means that 4 there needs to get converted into a 1. And I'm going to do this in a similar fashion to what I did a couple of steps ago. I'm going to take this row and divide by whatever it takes to make that a 1. So I'll divide by 4. So now this bottom row is, let's see, 0 divided by 4 is still 0. 0 divided by 4 is still 0. 4 divided by 4 is 1. 16 divided by 4 is 4. That's the only row that changes. The other ones, I'm just going to copy them down again because they're not changing right now. Now for the last step of this, really is only going to take one more step. Let me see if I can scooch this over just a little bit, make a little bit more room. There we go. So for the last step of this, I really only have one other thing I need to fix. Everything here looks pretty good, except for that -1 right there in that centered row. If I can get rid of that -1, then this will be exactly the diagonal of 1s with 0s everywhere else, just like it's supposed to be. So I'm going to take row 2, and I'm going to add 1 times row 3, because then I'll be doing 1 plus -1, and that'll kill off that -1. It'll turn it into a 0. So, oops, I scrolled too far. So now, the final result of this. Let's see. The top row doesn't change, because I'm not doing anything to the top row. I'll just copy it down again. The bottom row doesn't change, because it's not the source that changes, it's the target. And then I'm doing 1 times 0 added to 0. That's still 0. 1 times 0 added to 1. That's still 1. 1 times 1 added to -1. That's a 0, which was my entire plan all along. And 1 times 4 added to -3, which makes +1. So at the end here, think about, you don't always have to write this out, but think about translating back into equations. This top row would translate into the equation x plus 0y plus 0z equals -1. The second row would translate into the equation 0x plus 1y plus 0z equals 1. And the bottom row would translate into 0x, 0y, 1z equals 4. In other words, our solution is -1, 1, 4. That last column is the answer to the system of equations. So there's a lot of getting used to doing the arithmetic that you're going to have when you work with matrices, but you'll get good at it pretty quickly. The only other thing I have to teach you before you can handle the homework for this is how do you recognize with matrices when you get the weird kinds of answers? Because there are two weird kinds of answers you can run into. There's no solution, because that is a possible thing that you can have with a system of equations. And there's infinitely many solutions that you can also get with a system of equations. So here's how you recognize them when you're looking at a matrix. Remember that each row of a matrix represents an equation. Think about what the equations are actually saying, if you were to translate them back into equations. And if you're looking at a matrix that has a row like this, the translated version of this row says 0x plus 0y plus 0z equals 1. In other words, this row is saying 0 equals 1. And when you were back in Algebra 1, that used to be a warning that you had no solution. And it means the exact same thing now. Something like that means you have no solution to the system of equations. So that's what a no solution type of situation looks like. Now compare that to this one we've got here, because this has a rather important subtle difference. If you look at that bottom row, this bottom row says 0x plus 0y plus 0z equals 0. In other words, 0 equals 0. And back in Algebra 1, that used to mean that you would have infinitely many solutions. I suspect that back when you were in Algebra 1, almost everybody probably translated that into IMS and just abbreviated. And we're going to do the same thing here. If you write on a test IMS, I know what you mean. It means infinitely many solutions. And then there's one other little tricky question, and that is, what if you're working with a system of equations in a matrix, and you simplify the matrix and you get something like this? Because here, you've got one row that seems to be saying no solution, and you have another row that seems to be saying infinitely many solutions. So a pretty natural question would be, which one wins? Which is the proper answer? You can't have both. I mean, if there's infinitely many solutions, then there's no solution. So luckily there is a very, very, very simple rule. No solution always wins. If you have any row of your matrix anywhere that indicates no solutions, it doesn't matter what's happening anywhere else. Even if another part says infinitely many solutions or something, doesn't matter. No solution always wins. Every time.